you have T also has a fixed point. Right. So if that is at times it is useful to have it is easy to show that T power k has a fixed point, or T power k is a contraction, therefore it will have fixed point. Therefore this consequence of this this one will tell us that T also has a fixed point. So why is that? That is because if X is a fixed point of if x naught if X is a fixed point of T power k, then you have the X is going to be the limit n tends to infinity of n of n or n plus 1, or you can write Tx naught. It will be the same thing. Whether you write x naught or Tx naught, it is going to be the same thing because we are taking n tends to infinity. So it is going to be the same thing. So this is going to be because now T is continuous and it's an operator, so you can write this as T limit n tends to infinity of T of T power k n to x naught, and that is since T is continuous, we can write this limit inside. The T comes out of this. So, and we know that T power k has a fixed point, therefore this is nothing but Tx. So this shows that x is equals to Tx. So if x is a fixed point of T power k, then that is also a fixed point of T. So now let's go back to our initial value problem. So we had the initial value problem, the Picard's.
So
yes, yeah.
Why we take particular point x naught Tx naught?
It's the same thing, right? So whether you take T, it is going to be plus 1, right? So
No sir, why मतलब हमने Tx naught पे क्यों वो किया, मतलब x equals to
no, I'm saying x is equals to the limit of T power kn. Also it is T power kn, also it for n plus 1 or for any other n, right? So I can write this as Tx naught. And you, instead of starting with x naught, you are going to start with Tx naught. It's going to be the same. If it has a fixed point,
that means x naught. That means x naught is the general point.
Yeah, that's what we said, right? X naught is any point.
Yes.
You start with any x naught, it is going to be the if it has a unique fixed point, then it's going to convert to only that say fixed point. Whether you start with x naught or you start with y naught or Tx naught, anything. Right?
Yes.
Yeah. So now let's go back to our Picard's theorem. So what was the Picard's theorem? We had an initial value problem, and then we had we have taken a rectangle. This contains the points t, x, where mod t minus t naught less than or equals to a, and mod x minus x naught less than or equals to. And then we showed that, and then we had another quantity, that is the minimum of a comma b by m, where m is the maximum or the supremum of mod f over this rectangle R. Then we showed that there is a solution in the neighborhood of T naught, that is T naught minus h2 T naught plus h. So now let us show this by the fixed point theorem. How this fixed point theorem is giving us a proof, very simple proof for this. So consider the space X, which contains the set of all continuous functions, okay, in T naught minus H2 T naught plus H, okay, such that these functions are bounded by this, okay, for mod T minus T naught less than or equals to H. Okay, so this is now a subset of the set of continuous functions, and therefore you can use the metric D of Fg, which is the maximum over mod T minus T naught less than or equals to H of mod Ft minus Gt. Okay, so then this X with D becomes a metric space. It's in fact a closed metric space, therefore it itself is a complete metric space. So these things you can show yourself. It becomes a closed subspace of subset of C. So self is a complete metric space. Then we define the operator. So using the fixed point, using the Picard iterations. So define this to be T naught to T of F S Xs. Okay, that is, we are taking the point at the function X, and that defines a function Txt using this relation. And this T, now the T is actually from X to X. So why is that? What is X? X is shows that it is a continuous function. That is not difficult to show. And we only have to show that xt minus x naught less than or equals to b. If I show that for t, then we have, that is, you see that t is now tx is a continuous function because f is continuous. We assume that it is f is continuous. Therefore, the integral of that is going to be continuous. Therefore, tx is continuous. So for any x, tx is continuous. Therefore, tx, and moreover, if you write this tx minus x naught. Okay, so that is going to be mod T naught to T of F. So this is F is less than or equals to M, we know this, and mod T minus T naught, which is less than or equals to M into H, which is less than or equals to 1. Therefore, Tx belongs to X. So T is now an operator from X to X, and right. Moreover, we can show that it is also a continuous operator. That is because if you have xn converges to x uniformly, this integral will converge. Right? So you can write xn converges to x uniformly. Implies f of s xn converges to f sx uniformly, and their integrals also. Okay, so this implies that txn converges to tx. So that shows that t is also a continuous. Now we show that t is also a contraction. So t is not contraction. We'll show that t power k has a fixed point. So let us try to show some more calculations in the lines that in the process of showing that t power k is a contraction. So let us estimate contraction for some k. Let me take k to be large enough. So for this, let us first do the tx1 minus tx2. Take x1 and x2. This is going to be less than or equals to t naught to t f sx1 minus f sx2. This x1 and x2, these are all functions. Okay. So this is now since f is ellipsis continuous, so this is going to be less than or equals to L times T naught to T of mod x1 minus x2. Okay. So again, we can write this to be less than or equals to L into the maximum of over mod T minus T naught less than or equals to H of mod x1 minus x2 times mod T minus T. Okay. So this is my L into mod T minus T naught is less than or equals to H times this what we wrote as d of x1 x2, right? And now on the left hand side also you take the maximum over mod T minus T naught less than or equals to H. Okay, then we get the d of Tx1 Tx2 less than or equals to LH into d of x1 x2. If LH is less than 1, then this becomes a contraction. Okay. If LH is not less than 1, okay, then we proceed further. If LH is less than 1, then T is a contraction. If not, then apply the same thing for T square. T square x2. And this is going to be L H square by 2 to d of x1 x2 and so on, and therefore t of tk x1 tk x2 will be less than or equals to LH. Okay. Of course, this calculation I am not showing you, but if you write t square and this thing, then you get an integral, and then integral. These calculations are done in the same calculation type of calculations you will have to do in case of this. Therefore, you get when you integrate t minus t naught, you get t minus t naught square by 2. That's where you get the 2 by factorial k into x2. But you know that this actually goes to 0 as k tends to infinity. So that shows that for k large, you can actually have a constant here which is less than 1. Okay, therefore t power k is contraction. So we showed by remark that t power k is contraction, therefore t power k has a fixed point and hence t has a fixed point. And t has a fixed point, that shows that t has a fixed point means how did we define the t? T is defined like this, right? Tx. So if Tx equals to x, then we have the, right? So Tx equals to x means that x is a solution. That's what we saw, the integral equation. So it is just whatever the Picards proved in the abstract sense, this is what we have. The whole thing, we just need that existence of a fixed point. Okay. So in the Picard iterations, we required that these sequence xn converge. Okay. That's where we have we first showed that xn is a Cauchy sequence and therefore converges and things like that. But if you see the what we reduced our problem to is only the, you can see this problem as two different problems. One is existence and the other one is uniqueness. Okay. So now the question is that if ellipsis continuity is dropped, is dropped, okay, can we get the existence? can we get the existence. We have seen earlier that there are some examples where you can get the uniqueness even if you don't have the ellipsis condition. There are some techniques from analysis can be used to get to argue for the uniqueness even if the function is not ellipsis. Okay, so now the question is, if the ellipsis condition is dropped, whether we can get the existence. So this is answer is yes, and this is the Peano's theorem, which says that continuity of f is enough. Okay. If it is continuous, then there exists a solution. So now let us try to show this. So the idea to show this is using the fixed point theorem, using the fixed points. So what we see in the fixed point theorem is that if you have a contraction map, then you have fixed point, unique fixed point. The contraction actually gives existence as well as uniqueness. Again here, if we drop the uniqueness, can we get the existence? So that's what we have seen in case of calculus wave when we use the intermediate value theorem, also that just the continuity is enough. So similarly, what is that we require here to show the existence of fixed point? So I need some more elements from the real analysis. One is the sequence that we define. Okay. If it has a subsequence that converges, that is enough. So first observation is that we do not need, we don't require the convergence of the whole sequence. Enough to have convergence of sequence, enough to have a subsequence that converges. Right? If a subsequence converges, we can pass through the limit. If a subsequence converges uniformly, then you can pass through the limit in the subsequence. How does it matter whether it is a sequence or subsequence to get the limit? Because we are only interested in the limit. Okay, as we are interested only in the limit. We are interested in the limit only. The limit function only we are interested. We are not interested in what is each element of the sequence going to be look like. Right? So we know from our calculus that this one, in case of real sequences, we know that if a sequence is bounded, it has a convergent subsequence. Okay. So in case of real numbers, okay, boundedness implies convergent subsequence. So this is the Bolzano-Weierstrass theorem, right? But and if you see in case of these xn's are bounded is a very simple thing. What we do, how we define the xn's? Xnt, we define this as x naught plus right. This is how we define. So just write xnt. It becomes simply this. So this is less than or equals to mod x naught plus f is anyway bounded. We have into mod t minus t naught. This already we did the calculation, right? Mod x naught plus m into h, which is less than or equals to mod x naught plus the b. So this shows that x and t are uniformly bounded. So it's not difficult to show the uniform boundedness of the sequence. So does it imply that convergent subsequence? Does it imply the convergent subsequence? The answer is no. And this is known as the compactness. So I'm not going to do the complete details of this compact thing, but I will do some details. Compact subsets or subsequences subset or subsequences are the same. Subsets of the C I. I is, I'll take very simple a case where I is an interval which is close bounded interval that we have something like this. That is enough for us. Okay, I is a close bounded interval. What are the compact subsets of CI? CI, we write the metric between on CI as T of ft as the maximum over I of mod ft minus gt. Okay. Bounded subsets we know, right? So bounded subsets we know, that is uniformly bounded subsets. And so this is what is the compact? A set, no? A set, a subset or a family. We call like this is compact if A is bounded. This anyway we require from the Bolzano-Weierstrass kind of thing. And another thing is that it is equicontinuous. So this is a theorem which is known as Scalia-Zula theorem. So you will see this in your real analysis course, compact subsets of this. Okay. It's a. I'm not going to give the proof of this, but what is this equicontinuous? Equicontinuous means that you need for any epsilon greater than 0, there exists a delta such that whenever you have the mod x minus y less than delta, this implies fx minus fy is less than epsilon, and this condition should happen for all f in the class E. So that is for every function we define this delta, but now this delta is independent of f. So when delta is independent of f, so then we say that this continuity is equicontinuous. So that is, if A is a equicontinuous family and if A is uniformly bounded, then it is A is going to be compact. Okay, so what are the compact subsets? So we know the bounded sequences like that. What are the compact subsets? Some examples I will give. Suppose you have a sequence, say UN, such that UN T is bounded for all T, and also its derivatives for all T. Then UN is compact. So the boundedness, anyway, the UN is T less than or equals to M for all T. This implies boundedness. Okay, so this implies boundedness. Right. Now the equicontinuity comes from the mean value theorem. So the mean value theorem tells us that you take UN T minus, say, UNS. The mean value theorem, this is going to be UN prime at a point Z times mod T minus S. So this is less than or equals to M into mod T minus S. So given any epsilon greater than 0, I can choose delta to be epsilon by M. So given any epsilon greater than 0, so choose delta to be epsilon by M. Then this is going to be less than epsilon by M into M, which is epsilon. Okay. Then you get the equicontinuity of this UN. So this implies UN is equicontinuous. So these are the some general properties of sequences where you have an example set of a class of sequences which are compact. Okay, so also there are many other examples that you can see, but for us this is enough. This example is enough for our purpose. Okay, so there is another fixed point theorem which is on this using these concepts. So again, the proof of this I am not going to do. So this is this says that at AB compact, convex subset of C. And T is an operator from Ci to Ci. Such that TA is contained in T. Then T has a fixed point. Not unique, fixed point. So this doesn't give the uniqueness of the fixed point, but it gives existence of the fixed point. It gives existence of fixed point. So I'm not going to give a proof of this, but this requires more analysis. So convex, I guess you know what is the meaning of a convex set. Right? The convex means that A is convex. Okay. Means that if you take any two points in A, the line joining these points 1 minus t to x2 also belongs to A. So such a set is called convex set. Okay. So if you have a subset which is a compact subset, okay, and a convex subset, and if you have the map T, which is actually taking the TA2 inside the TA. Okay, so this is how we are reducing the contractions. You see, some sense TA contained in A has contraction, but it's not if and only if. See that if it is contraction map, then this follows. But if this is there, then you can't say that it is a contraction map. That's the idea here. Okay, okay, so now we will use this theorem. So going to proof of Piano's theorem. So we assume that this we can take this m to be greater than or equals to 1. What is m? M is the supremum of this over R of this mod f. Okay. R is defined. I already said what is R. So we will take R to be here, the set of points t comma x with mod t minus t naught less than or equals to less than or equals to A, and mod x minus x naught. Take this also less than or equals to A. So I'm taking the same A here. It doesn't matter, you take the smaller of these two. If A and B are there, take the smaller of these two. Then this H also becomes A. The H becomes minimum of A, B by M. So this is going to be A by M. So this is going to be A by M because M is greater than M. Now we define the set A. Define the set A. Okay, so U, which is this continuous functions, so that ut minus x naught. So this is the same as what we had earlier. Ut minus or x minus x naught is less than or equals to b we have. So since we are taking A to be the B, so less than or equals to A. And we add one more condition which is T1 minus U2. This is also less. This is less than or equals to M into T1 minus T2. So now here, if this is the case, then you can show that A is compact because I am putting the same, both conditions are here. So the first condition shows that U is uniformly bounded, and second condition shows that it is U is equicontinuous. Right? So therefore, A is compact, and also it is closed. Sorry, and also it is convex. Closeness anyway is there. Also it is convex. If U1 and U2 are there, then you can show that U1 minus U2 is also there. Right. And on this set A, on the, now we can define, we can see what is happening with T. T is what we define, X2 or Ci to Ci. So how do we define that? Tx equals to x naught plus E naught to T of f ts Tx. Now if Ta is contained in A, then we are done. Ta is contained in A, then we are done. Okay. Why Ta is contained in A? So we have to show that for the map T for U in A, Tu also satisfies this these two conditions. Tu satisfies this and this. So take the Tu as a function of T and write this one. So this is going to be less than or equals to. So all the same calculations which will come again and again. So this is MH, which is less than or equals to. And write the T U at T1, the second condition. Okay. So during the using the domain decomposition property of this integrals, this M into T1 minus T2. So this implies that Tu belongs to. Therefore, T has a fixed point. So this implies T has fixed point. So what we used here is only that the whole thing. We know where we used the ellipsis continuity. We just used that this M exists. That's all. That's the only thing that we used. Okay. That is f is actually continuous and bounded function. If f is not continuous, then we have difficulty in differentiating the integral equation. So therefore, we require the f to be continuous. So that the limit function actually becomes a solution of the differential equation. Okay, do you have any questions? No questions. Okay. So now again, the a question about the once we do this, is continuity necessary? Is continuity of FTX necessary for existence? The answer is no. For example, I can take we can take the function f prime equals to f y, the y at 0 is 0, and fty is a function which is, we know that these functions t square plus y square when t and y not 0 0 and 0 when t and y is identical to 0. We know that this function is f is not continuous. F is not continuous in two variables, but y equals to 0 is a solution. Y equals to 0 is a solution of the initial value problem. So therefore, the continuity of this f is actually not a necessary condition even in the Pianos theorem. What we saw in the earlier that ipsis continuity is not necessary. Now even continuity is also not necessary. There can be examples where even if f is not continuous, you may have the solutions. But it gives, the Pianos theorem gives the sufficient condition. If f is continuous, then you always have a solution. Okay, so you would have done some examples in your tutorial classes. I've done some examples of non-ellipsis continuous functions and their solutions.
Not yet, sir.
No, sir.
Okay, let me do one example. Say, for example, I take y power half with y at 0 is 0. Okay, so you can use the separation of variables and to solve this equation. And you see that if you take any rectangle around y, where mod t less than or equals to say a and mod y less than or equals to b, then see that f ty, which is y power half, or you can take mod y power of half, and write y power half of mod y power half is not ellipsis. How do we show this? It is not ellipsis in any rectangle containing the origin 0. Why is that? Is because you take ft by 1 minus ft0. So this is going to be mod y1 power half. Okay. So if this is ellipsis continuous, then this has to be less than or equals to L into mod y1. Right? Yes.
Yes, sir.
Yes, this is true. Then you divide by 1 and take limit. So we will have the limit of so we will have the left hand side, you will have mod y1 over half by mod y1 is less than or equals to L, which is not true. Okay, so this is not bounded. Left hand side goes to infinity and right hand side is L. Therefore, this function is not ellipsis continuous. Therefore, the uniqueness fails here. Therefore, uniqueness fails. Uniqueness fails means by the this is not ellipsis continuous, so the uniqueness may fail. We say that way. Uniqueness may fail. Because I said that's only a sufficient condition, not necessary. Therefore, uniqueness may fail. And mod y power half is a continuous function. Therefore, by Peano's theorem, there exists a solution. And you can see that easily that y equals to 0 is a solution. Okay? It's a trivial solution. And another solution also you can write that is x squared by 4, which you will write by separation of variables. Right. So if I write y prime, it is going to be x by 2, and power half is going to be x by 2. Okay. So this is you get by separation of variables. So what's happening here? So it is 0 is a solution, and the other solution is x squared by 4. Okay. So this is the solution.
Cancel theorem बना सकते हैं.
Huh? Yes.
X minus alpha to the power 2 also solution for all alpha belongs to R.
Yeah. For alpha
Belongs to R.
So y alpha. So we are using t. So let me write. So what you said, t minus alpha square by 4.
T minus, yes sir.
So this is also a solution. That's what you're saying.
Yes.
Right. So this is for any alpha, right? So for any alpha. Therefore, what we are seeing here is that when we have two solutions, okay, then we are able to show that there are infinitely many solutions, not infinitely many. How many such solutions are there? They are not countably infinite. They are uncountably infinite solutions are there. For every alpha which is a real number, there is a solution. So that shows that the set of solutions, okay, the set of solutions, okay, the set of solutions is the cardinality of that is same as the cardinality of the interval. Okay. So that is a continuum. This is called it is a continuum. So what would ask the question? A general question. What could be a general question here? Can any of you tell me? That is, if uniqueness fails, okay, then there exists a continuum of solutions. Is the following statement true? Okay, that is, if uniqueness fails, okay, then there exists a continuum of solutions. Continuum of solutions means that there are uncountably infinite number of solutions for this problem. The linearly independenceness is doesn't matter here. It doesn't make any sense because these are nonlinear equations. Okay. So that means that either you have uniqueness or you have continuum of solutions. You don't have anything in between. You don't have an initial value problem with f to be a continuous function. Okay. With f to be a continuous function, so that the problem has exactly two solutions. It doesn't happen. The situation doesn't happen. Or exactly has three solutions. Or exactly has 100 solutions. If the uniqueness fails, then there are uncountably many solutions. And this is a theorem which is known as the Kuznets theorem. He proved it for a more general class of dynamical systems, but for initial value problems, it is a easy consequence. Can prove it easily. So let's see how does one prove this. The proof is very simple. See, the very simple observations lead to such kind of a strong assertions. Okay. Suppose you you take a problem with the initial value problem and you have a solution starting at t0. You have, say, you have two solutions. So you can take the existence of two solutions. One is x1 and the other one is x2. So let me call this a sigma, and this is one solution, x1. Okay. And you have another solution, say x2. At this point sigma, they are different. Take a point where they are different. It need not be very large a faraway point. It can be a point very close to T0. Some point sigma where it is where this x1 is different from x2. Okay. So in T0 to sigma, okay, x1 T and x2 T are two solutions. Once we have this, and we are starting with an assumption that f is a continuous function, and you choose a point here. I call this as eta, lying between these two. Okay, so this is x1 sigma. So x1 or x2 sigma, and this is another one, x2 sigma. Or you write 0 in the notes. Yeah. So choose eta such a way that x1 sigma is less than eta less than x2 sigma. Now with this eta, I can solve the initial value problem. Now consider the problem x prime equals to f dx with the x at sigma equals to eta. Solve this problem because now f is a continuous function. By Peano's theorem, there exists a solution for this problem. So there is a solution for this, right? So let me write that solution. Okay, that solution in a neighborhood of the sigma, right? So it will have a sigma like this, a solution like this. And we know that you can extend the solution further. If it is not a closed interval, you can extend the solution. And look at the function. Look at when it is extended, it is going to either touch x1 or x2, or it may not touch also. It may come to T0. Yeah, it may come to T0. That is another solution. See, for every eta there is a solution. If it touches this x0, if it touches this x1, say at this point, then you take another solution, which is say z, which is defined as, okay, this one before this point and this one like this. Okay, so take this one, take this as a solution. Okay, that is going to be x1 when t is less than, say, t1. So call this point as t1, and so let me call it as y. This one as y for t greater than t. Then z is a solution of the original problem. So z also satisfies the same solution, same equation as x1 and x2. So then z is another solution. See, and z is a third solution. And now I can write this kind of solutions for every eta that is lying between x1 and x2. And how many such etas are there? It's an interval. The x1, x2 is an interval. So the number of etas are there are uncountably many. It's the same as the number of elements in the interval. So for every eta in this interval, okay, so therefore for every eta in x1 sigma to x2 sigma, okay, there exists a solution. Of x prime equals to f dx with x at t0 equals to x0. So that means first we assume that x1 and x2 are the two solutions of this, and then we get for every eta in between these 2 points there is a solution. Therefore, the number of solutions are uncountably many, or the solution set is continuous. See, what is the consequence of this? Consequence is that if you have an initial value problem with f to be right hand side function, which is a continuous function, then the initial value problem has uncountably many solutions. Okay. Any questions? No questions. Okay. So if you have no questions, I will stop it here.
सर इससे पिछली वाली स्लाइड को एक्सप्लेन कर दीजिए, मेरा नेट जल्दी से हो गया।
Last one.
Yes sir, इससे last.
So we started with the theorem which says here, I explained that if you take the problem x prime equals to f dx, okay, f is a continuous function with x at t naught equals to x naught. If there are two solutions, then there are uncountably many solutions. Or two solutions, then there exists infinitely many. Let me see how this is proved. Take a point eta between x1 and x2. Okay, and with that eta as initial condition, we have a solution because f is a continuous function. Because f is a continuous function. Therefore, by Peano's theorem, there exists a solution. And once if there is a solution, a local solution. Right? So again, go to the end point and then keep extending the solution. And this extension of the solution, it has to touch either x1 and or x2. If it doesn't touch, then it will come to t naught anyway. Okay, then that becomes another solution. If it touches, then you define z to be this piece. It touches the point where it touches, and this piece where it doesn't touch. Okay. And then this one z becomes the solution because it has two pieces, and you are smoothly contained because this is a differentiable function. You are containing this. Therefore, the left derivative, right derivative, you can see that they are well defined and they are going to be equal because this x is going to be the same when the point where x at t1 and z at t1 are going to be x at t1, y at t1 is same. So you can show that z is a solution. Therefore, this z now becomes a third solution. And how the z is coming? Z is coming with an initial condition eta. So now I can change eta. Take eta 1, eta 2, eta 3. So each one you have one solution, z1, z2, z3. So it's a very simple observation. But actual Kurzweil's theorem says for dynamical systems, which is which is a little more complicated to prove that, and it requires many more things. But for ODEs, for simple equations like this, we can easily prove this. That's what it is. Okay, so next class I will introduce something more analysis. So if you have no questions, I will stop it here.